Every curve at 200 miles per hour generates a lateral force equal to 80% of gravity. Physics, doing everything it can to throw a train off the rails. Steel expands, wheels oscillate violently, tolerances shrink to fractions of a millimeter. And yet, across 60 years and 10 billion passenger kilometers, the Shinkansen has never lost a single life. The reason starts beneath the wheels, with the track itself. Jointed track, the kind built from short, bolted rail segments, set a hard speed limit for trains. Each passing wheel slams into every gap, sending a shockwave through the car and the track. At 100 miles per hour, the pounding becomes a blur. Push to 200, and these impacts would destroy wheels, rails, and any hope of stability. The solution is continuous welded rail, or CWR, steel rails fused into single lengths that stretch for kilometers without a break. Every weld is made at a carefully chosen temperature, usually around 30 degrees Celsius for the Shinkansen. This is the neutral temperature, the point where the rail is neither stretched nor compressed. Install a 25-meter rail at this temperature, and a 20-degree swing will lengthen it by about 6 millimeters. Multiply that by the full length of a high-speed line, and the forces become immense. Instead of letting rails expand freely and buckle, engineers clamp the rail to the sleepers and anchor everything to the foundation. The entire track structure absorbs the stress. Sensors monitor the rail's internal force, and if temperatures run too hot or cold, speed limits are imposed before trouble can start. Hideo Shima, the Shinkansen's chief engineer, once wrote that a single rail joint at these speeds is an invitation to disaster. By eliminating every joint, CWR turned a century-old weakness into a foundation for safe, smooth, high-speed travel. The rail becomes a continuous, tensioned ribbon, one that can withstand both the pounding of a 200 miles per hour train and the slow push and pull of Japan's changing seasons. Concrete slab track changed the foundation of high-speed rail. Before 1964, most tracks relied on crushed stone ballast, a bed that could shift, settle, or deform under repeated loading. For the Shinkansen, Hideo Shima and his engineering team demanded something stiff, something that would not flex under the immense forces of a 200 miles per hour train. They specified a continuous reinforced concrete slab with a vertical stiffness between 80 and 120 gigapascals, more than double that of traditional ballast. This slab supports the rail and sleepers directly, limiting vertical deflection to less than half a millimeter, even under 800 kilonewton lateral loads generated on curves. The geometry of the track itself was just as radical. Instead of abrupt bends and short radius curves, the 1964 Shinkansen line introduced a minimum curve radius of 4,000 meters. This decision meant that centrifugal forces remained manageable, and super elevation, raising the outer rail, could be applied gradually. Engineers used spiral transitions, or clothoids, to ease trains into each curve, keeping the rate of cant increase within a strict limit. No more than 0.2% per 100 meters. The result was a track geometry so precision that the lateral and vertical alignment could be measured in tenths of a millimeter. Hideo Shima called this approach a clean slate. By breaking from the compromises of mixed-traffic railways, the Shinkansen's foundation became the first line of defense against derailment. The slab's stiffness, the smooth spiral transitions, and the sweeping curve radii all combined to create a base where higher-order problems, like dynamic instability and wheel-rail oscillation, could be tackled with confidence. This was not just an upgrade, it was a new standard for what a high-speed railway could be. In 1955, a French prototype train pushed past 180 kilometers per hour on a straightaway near Orléans. What should have been a triumph nearly ended in disaster. The wheel sets began to sway side to side in a rapid, self-reinforcing motion. what engineers soon called hunting oscillation. Lateral acceleration spiked to 0.3 g, and the entire train started to dance on the rails, as Chief Mechanical Engineer Marcel Dufour later wrote in his notes. The cause lay hidden in the geometry of the wheels and rails. At low speeds, the conical profile of the wheel, treads, keeps the train centered. But as speed rises, this self-steering action can flip into instability. The wheel sets begin to oscillate at a frequency around 1.7 Hz, and with each cycle, the motion grows stronger. Without intervention, this phenomenon could have set a hard ceiling on high-speed rail, making 200 miles per hour an impossible dream. The solution arrived in the form of a mechanical device, the yaw damper. Mounted between the bogie frame and the axle, the damper resists rapid twisting, or yaw, with a carefully tuned hydraulic force. The required damping coefficient for stability at 200 miles per hour is about 1.8 times 10 to the 5th Newton-meter seconds per radian. With yaw dampers installed, the hunting threshold jumps well above 340 kilometers per hour. The French TGV, German ICE, and Japanese Shinkansen all adopted this technology. On test tracks, lateral accelerations dropped by 90%, transforming a fatal flaw into a manageable vibration. The yaw damper became the silent guardian of high-speed rail, holding chaos at bay with each passing kilometer. At 200 miles per hour, physics draws an unforgiving line. The outward, or centrifugal, force on a 100-ton train rounding a 4,000-meter curve reaches 0.815 times gravity, about 800 kilonewtons pressing against the outer rail. This force is not theoretical. It is calculated directly from the equation AC equals V squared over R, where V is speed in meters per second and R is the curve radius. At 89.4 meters per second and a 4,000-meter radius, the math yields nearly 8 meters per second squared. If the track offered no resistance, the train would simply leave the rails. To counteract this, engineers rely on super elevation, raising the outer rail above the inner. The formula for equilibrium cant, E equals V squared over GR, gives a required cant of 204 millimeters at these speeds and radii. But in practice, the maximum safe cant is closer to 150 millimeters. That leaves a gap, a cant deficiency of 54 millimeters. High-speed lines accept this shortfall, allowing a controlled amount of lateral acceleration to reach the passengers, but never enough to threaten stability or comfort. Even with yaw dampers suppressing hunting oscillation, a significant lateral force remains unbalanced. The 800 kilonewton load must be distributed across the rail and the supporting structure. This is why minimum curve radii are non-negotiable, and why every increase in speed demands either a wider curve or more advanced solutions. The numbers define the boundary between safe passage and derailment, and set the stage for technologies like active tilt to close the remaining gap. Active tilt technology transforms the physics of high-speed rail. On the N700 Shinkansen, electro-hydraulic actuators can tilt each car up to 8 degrees, creating the equivalent of 130 millimeters of extra cant, essentially bending the laws of geometry in real time. When a 300-ton train enters a 4,000-meter radius curve at 340 kilometers per hour, sensors immediately detect the lateral acceleration. Inertial measurement units and GNSS data fuse together, giving the system a precise reading of speed, position, and curve radius. The control computer runs a PID algorithm, calculating the target tilt angle and adjusting hydraulic pressure with a response time of just 0.3 seconds. This rapid feedback allows the train to lean into the curve, reducing the unbalanced lateral force that would otherwise push passengers against the outer wall and threaten wheel-rail contact. The actuators themselves are engineered for both power and precision, using double-acting cylinders rated for 25 megapascals. The control loop is constantly correcting for any difference between commanded and actual tilt, using real-time data to anticipate upcoming curves from a preloaded geometry map. Safety interlocks monitor lateral acceleration, ready to override the system if the forces exceed 0.2 g. By combining mechanical muscle with advanced sensor fusion, the N700's tilt system lets trains run faster through tight curves without sacrificing stability or comfort. This is not just a workaround for cant deficiency, it's a dynamic solution that rewrites the speed limits of conventional rail physics. Dr. Yellow glides through the night, not as a passenger train, but as the Shinkansen's most vigilant guardian. Inside, a battery of laser profilometers sweeps the rails, measuring the track's alignment and height to within plus or minus 0.05 millimeters, less than the thickness of a sheet of paper. Every week, these sensors scan hundreds of kilometers, searching for the faintest deviation. If Dr. Yellow finds a misalignment greater than 0.68 millimeters, a repair crew is dispatched before the next morning's first train. In 2019, a 0.68 millimeter dip on a 2-kilometer slab track section triggered a full intervention within 48 hours. The margin for error at 200 miles per hour is measured in fractions of a millimeter. The system's vigilance is tested by extremes. During the August 2018 heat wave, track sensors recorded a 12-degree temperature spike, pushing compressive rail stress to 45 megapascals. The response was immediate. Speeds were cut, cooling crews deployed, and operations resumed only after every reading returned to normal. These procedures are not theoretical. Since 1964, the Shinkansen has carried over 10 billion passenger kilometers without a single fatal derailment or collision, a record unmatched by any other high-speed rail network. In the United States, the Asila's monthly inspections and older ballast track have led to repeated speed restrictions. China's CRH system, while vast, has reported 2 non-fatal derailments linked to rapid construction and settlement. The difference is not just technology, but the relentless pursuit of precision. On the Shinkansen, safety is enforced not by luck, but by a laser's certainty and a culture that treats a tenth of a millimeter as the boundary between routine and risk. Every day, high-speed trains prove that meticulous engineering can master even the most unforgiving physical laws. As nations race to modernize infrastructure, the Shinkansen's record, over 50 years without a passenger fatality, sets a standard. Precision isn't just technical. It's the difference between possibility and disaster. Thanks for watching.